Hello everyone. Are you all able to hear me? Please can you all confirm? Let me use a poll question here on are you all able to hear me? Yes or a no? Please can you respond to this on whether you're able to hear me or not? If you all are able to hear me, then we can proceed further. Wonderful. 93% of y'all are able to hear me. Wonderful. And I believe all of y'all now have learning management system access. Okay, but we will do a quick giveaway in terms of the quiz that you have taken, for which Enoch, can you please share your screen and quickly run the random number generator and let us give away the quiz winners?
Sure, Barney. Let me do that. So this is the list of all the people who have engaged with our quiz yesterday and who have answered. So we have serial number 1 till serial number 300. So we are going to use a random number generator to pick out one random number, and that person would be the winner of a lucky draw. All right, serial number 1 till serial number 300. So just ensuring that's 300 and it starts with 1. So let's do a countdown. 3, 2, and 1. So number 121. So let's see who that lucky person is. So we have Jayashree Lakala, and congratulations Jayashree, you are our lucky winner, and we will contact you most probably today itself. We are going to contact you and we will tell you further details on how you can access your lucky draw.
Yeah, Enoch, a few
Yeah,
duplicates exist. I think there are certain repetitions of certain names. Please ensure that those kind of things are addressed from tomorrow onwards.
I'll do that one.
Yeah,
Yeah.
sure. Congrats, Jayashree Lakala,
Yeah.
and you'll be contacted by us, and you'll be receiving a coupon. Great, and nice to see that you all are contributing. Now, everyone's name will be there. Don't worry on whether your name is there or not. Everyone's name will be there. Okay, and we don't selectively choose people. We take all the numbers, all the people who responded. Yeah. Okay, let us now proceed further. Even before there are some questions which are not so relevant. So here we have a drop down. We have AI and deep learning. And what did we cover until now? Let me quickly do a recap. We discussed about project management methodology, which is used in handling any of your data mining projects. It could be data science, it could be machine learning, it could be deep learning, does not matter, right? The end point is we need to have a structured approach in handling the projects so that the success rate of your projects more or less increases. And that's CRISP DM, cross industry standard process for data mining. In this, the first step is understanding the business problem. Once you understand the business problem, you need to record your business objectives and constraints. Then you proceed further with data collection. Even before you move on with data collection, you should be aware of the various data types: continuous, discrete, qualitative, quantitative, structured, unstructured, so on and so forth. Of course, as part of our the data science training, we get into the depth of imbalanced data sets. We explain about all these various imbalanced data sets, rare events. How do you define cost associated with each and every misclassification and all that? But for AI, we assume that that basic understanding exists. Okay. If not, then you might have to groom yourself on that aspect also. When it comes to data collection, we have primary data collection and secondary data collection. Also, we have data cleansing. Data cleansing or data preparation or exploratory data analysis or feature engineering. All these are different terms which can be interchangeably used. As part of data cleansing, data preparation, munging, wrangling, etc., you have a lot of these techniques. And then we have exploratory data analysis and feature engineering. Once you're done with this, we need to proceed further with data mining or machine learning. Before we proceed further with machine learning, we have actually taken a slight detour in understanding the mathematical foundations, in which we have covered data optimization aspects. Rate of change is also called as derivative or slope, and we have looked at a few of the rules of derivatives, such as the power rule, constant multiple rule, sum rule, difference rule, product rule, etc. And then we have had a procedure, or we have discussed about a procedure which will help you find the minima or maxima. One second. Now I can zoom it. Okay. If you have a single argument function, then we found the first order derivative, equated it to 0, and then found the critical values. Then we perform the second derivative test to decide on whether the values that we found. Okay, I think this is incomplete, my bad. So here, let me write. When it comes to second derivative test, if you get a positive value, then the critical value that we found would be called as minima. If the second derivative test gives you a negative value, then the critical value that you found would be called as maxima. This is when you have a single argument function. But then if you have multiple arguments, then how do you handle it? If you have multiple arguments, then you first find the first order derivative, equate it to 0, and then find the critical values. Once you find the critical value, then we need to decide on whether the critical value is minima or maxima. For that, you first take the first order partial derivative, then find the second order direct partial derivative and second order cross partial derivative. Yeah, and then we discussed about Hessian determinant F11, F12, F21, and F22. You need to cross multiply and subtract to get Hessian determinant, which is F11 into F22 minus F12 into F21. According to Young's theorem, you know that F12 is equal to F21. So these two will be the same. If this D value is going to be less than 0, then it would be a saddle point. What will be a saddle point? Your critical value would be a saddle point. Okay. What is a saddle point? From one direction, it will appear as if you have a minima. From another direction, it will appear as if it is a maxima. So you cannot conclude on whether your critical value is minima or maxima. If your Hessian determinant is greater than 0, D greater than 0, then there are two additional conditions that you need to check for. Number one, if A value is also greater than 0. What is A? This part, F11. If this A is also greater than 0, then your critical value is a minima. It's a minima. If D value is greater than 0 and if A is less than 0, then you get a maxima. Okay, then the critical value is called as maxima. This is how you conclude on whether the critical value that you found is a minima or maxima. And why do we take the derivative and equate it to 0 to find the critical value? Because critical value is that value where the slope is 0. Slope is 0. And you know that slope is nothing but derivative. Hence you find a derivative and equate it to 0 because slope is 0. But this critical value can be a minima or a maxima. We don't know, because the curve can be like this, right? If the curve is like this, you can have a minima or a maxima. Okay. This is what we have discussed, and then we discussed about Python basics. Today, we are going to discuss about deep learning primer. And if you go to AI Spry, you all must be having access to the learning management system now. Just click on this. The moment you log in, you'd be seeing this kind of a screen that you see. You do a drop down here and click on My Courses. The moment you click on My Courses, you will see AP State Skills Development Corporation and 360 Digit MG Faculty Development Program. You need to just click on that. The moment you click on that, you will see various modules. Module 1, Module 2. I think we have renamed these modules as with the topic names so that it's easier for you to understand on what are these modules. Now we are going to start with deep learning primer. A few additional things also are given just for your own practice. Okay, so 1, 2, 3, and then we'll be off to the practical world. Okay, even here we will be looking into the practical stuff. So deep learning primer, alongside you will also observe quiz. This quiz is only for your practice. So you just click on that and proceed further. These are the various things that we are going to discuss as part of today's discussion. So let me go to deep learning primer. So let me, yeah, go here and then we will discuss in further detail. What is deep learning in the first place? So as I've given you this onion peel example, the outermost peel is your artificial intelligence system. Within AI, you have something called as data science. Within data science, you have something called as data mining. Within data mining, you have submodules called as machine learning. Within that, you have something called as deep learning. And now the next big thing is reinforcement learning. And no matter what you do, at the end of the day, you will end up building an AI application. And there is another term which is synonymous to deep learning, which is neural network. Okay, neural network is synonymous, right? It's a synonym for deep learning. These two terms are interchangeably used. Sorry. So let's discuss about all of these in finer detail. All these slides, once again, would be there on your learning management system. Okay. The only thing is here, I need some animation in terms of explaining you, and that is the reason why I'm resorting to PowerPoint presentation. And there are a few questions on where will I find the previous videos, etc., etc. Yep. So let me tell you guys immediately that you have it here, and then there we go. Right. Today's session is live, and you have it. 6 videos. And all the videos, subsequent videos, will be uploaded here. This is a private channel, and you will have access, only you people will be having access to this. And I request you all to subscribe so that each time there is a new video that is uploaded, you are also notified about the same. Okay, first thing. Then what is the other question? Yeah. So, all right. So let's proceed further. Just give me a quick minute. Sorry. Just give me a quick minute. Okay, sorry about that. All right, let's proceed further. Um, okay, sure. So, scientists have come up with an architecture which was very similar to human brain. Human brain has neurons. I'm speaking now and you guys are able to hear me and understand because of neurons. Okay, because of neurons, you are able to understand and process the data. And this human brain is translated into an artificial system. This biological human brain has been translated into an artificial system with the hope that when we have an architecture which is very similar to human brain, then the architecture would behave exactly like a human would behave. And all your neurons in your brain are interconnected. On similar lines, in artificial system also, all of your neurons are interconnected. Neuron is a basic unit of processing information. You will have approximately 10 raised to the power 11 number of neurons in the human brain. And average number of connections per neuron ranges from 1000 to 10,000. And the communication speed is much slower. It is the order of a few milliseconds. Okay. And whenever you have a complex perpetual decision, okay, it would take just a few hundred milliseconds. And there is this 100-step rule, which says that any task which you do repetitively may not be passing through more than 100 neurons. Okay, it might not be passing through more than 100 neurons. So, however complex, however complicated the algorithm might be, right? Just in case you want to think about this as an algorithm, then however complicated or however difficult your algorithm might be, it will not pass more than 100 neurons. So at most, a human brain would be using 100 neurons for perpetual tasks. Now, another extremely important thing that you all should remember is that of compositionality. Okay, let me explain quickly here about compositionality. When you have your inputs, say image, human face, you're giving human face as an input to your network, assume. And this is your input layer. Input layer. Then your neural network will first take the image as an input and process it to the next layer, and this next layer is called as hidden layer. The first hidden layer, or this is the initial hidden layer. And your initial hidden layers capture the low level information. It captures the low level information. What do you mean by that? Say you have a human face like this. Okay. I'm not an artist, but ignore. And low level information could mean edges. So if you take an eye, there will be an edge here. There'll be another edge here. There'll be another edge. For nose also you'll have an edge. For mouth also you'll have an edge. For eyebrows also you'll have edges, right? For ears, for face, for chin, for head, you'll have edges. These kind of edges get captured by your initial hidden layers. Next, you'll have next set of layers. Initial hidden layers, then you'll have middle hidden layers. Middle hidden layers usually capture mid-level features. Mid-level features. Mid-level features means eyebrow of a person, eye of a person, nose of a person, mouth of a person, ear of a person. If you're probably identifying the parts of the face, that is that would be classified as mid-level features. And then you have the final layers, final hidden layers. These final hidden layers would be capturing the high level features. It would be capturing the high level features. High level features would mean you identify the entire face. Once you capture the high level features, then you go to the output layer and output the name of the face. Okay, you would output the name of the face. I mean, this is exactly how an attendance tracking system based on facial recognition is built. And if at all you people happen to visit Hyderabad, I welcome you all to visit our office to look at our robo and also look at the facial recognition system that we have built. Okay, and also you should visit Paradise to have biryani as well as explore our chatbot that we have built if you happen to be to Hyderabad. Yeah. All right. So this is how your neural network algorithm works. We will, of course, do a deep dive on what is this hidden layer, what do you mean by activation, so on and so forth. Just hold on to your questions for the next half an hour. For the next 30 minutes, hold on to your questions. Everything will become very clear. Okay, trust me on that. When you have unstructured data, such as images or audio files or unstructured textual data, then what you do is you take this unstructured data and you can do two things. One is you can either manually extract the features, or you can automatically extract the features. You can either manually extract the features or you can automatically extract. Manually, if you want to extract the features, then you can use techniques such as SIFT, shift invariant feature transform, or histogram of Gaussians, right? Or if it is speech related, you can use MEL frequency cepstral coefficient. Or if it is textual data, then you can use parse tree, syntactic techniques, so on and so forth, to extract the features manually. Once you extract the features manually, you use that on unsupervised learning techniques or supervised learning techniques. Okay, you apply either unsupervised learning techniques or supervised learning techniques the moment you extract the features. When do you do this? One is if you have limited data, if you have less data, because if you have less data, you cannot apply your deep learning algorithms, and only deep learning algorithms will help you automatically extract the data. So this automatic extraction is done by your deep learning algorithms, and your manual extraction is done by your shallow machine learning algorithms. When do you do manual extraction? When you have limited data. And second thing is when you need to interpret the results. What do you mean by that? Say we have an automatic attendance tracking system. Not we have, not say we have it. Okay. So what happens is the moment people start walking in, we have our CCTVs. These CCTVs will capture the face of the person, and it will recognize that this is employee 1 or employee 2 in that way. But then say your algorithm was tracking the entire human body, and it was looking at the hand and then classifying on whether this person is human or not. Okay, I'll not get into facial recognition system. Let me determine first that you want to recognize. Let me take a slightly different example here. Let me give you an example of a shopping mall. Okay, at the entrance of the shopping mall, say you have a CCTV, and this shopping mall owner wants you to recognize on how many people, how many humans entered the shopping mall. How many people have entered the shopping mall is what you want to recognize. If you're recognizing that this person is a human who has entered by looking at the hand, okay, versus you found out that your algorithm is recognizing that these people are humans by looking at the face, then which algorithm will you trust? Will you trust that algorithm which actually looks at the hand and classifies this person as a human? Or would you trust that algorithm which looks at the face and then classifies that this is a human? Okay, so let me put a poll question. That would be better. The poll question here is, how do you recognize that a human entered the mall? Or Say you recognize that a human entered a shopping mall. When will you trust the algorithm? When hand is identified in classifying that a human entered the mall, or when uh, when face is identified in classifying that a human entered. Okay, ignore if there are any spelling mistakes in that. Can you quickly respond? So that means you need some interpretation, right? You need to interpret. You don't want your algorithm to look at anything and then classify that that's a human. If you want such interpretation to exist in your model, then you go with manual extraction of features and proceed further. But then in certain scenarios, it is not easy to manually extract the features. It would be a tedious task. In those kind of scenarios, you go with automatic extraction. When there is no interpretation needed, and when you have a lot of data, that is when we go with deep learning. Interpretation is not critical. Okay, interpretation is not critical. Okay, in these two scenarios, you proceed further with automatic extraction. This is the same process that you follow when you deal with images or audio files or unstructured textual data. So when you have your shallow machine learning models, you manually extract the features, and then on top of that, you apply your algorithm to get the desired output. When it comes to deep learning models, we automatically extract the features. Now we will spend significant amount of time on this. Okay, so let us say that we have a specific data set. Very, very important. Next 30 minutes would be very important. Please focus. X1, X2, X3, X4, and X5. Say you have your output and you have your inputs 1, 2, 3, 4, and 5. Okay. Since you have 5 inputs, you have 5 neurons. This is called as input layer. This is called as input layer. Okay. And if you have 5 inputs, you'll have 5, and you also have another additional input. What is this input? Where is it coming from? If I give you this kind of an example, say you have red crosses and blue circles. Okay. And say you want to classify these two using a line. I mean, you can just draw a line and say that anything which falls above is red class, anything which falls below is blue class. When you have these kind of problems for which you can draw a line and segregate the classes, it is called as linearly separable boundaries or problems. Linear means a straight line. Okay, linear means a straight line. And what is the equation of line? Equation of line is y is equal to b plus mx or mx plus b. That's the equation of line which segregates. And this b is this B here. And it always doesn't have anything before that. That means it is as good as saying that you multiply this B with 1. If you multiply B with 1, you get B. Hence, this additional input neuron or node that you have will always have 1. This B is called as intercept. And this is called as slope. Similar to that, this B here in neural network is called as bias. And these W's that you see here, all these W's are called as weights. All these are called as weights like M. This is the reason why we have B and 1. All right. So I'll erase these and let us proceed further with more explanation. So when you have 5 inputs, you'll have 5 neurons. Okay, you'll have 5 neurons in your input layer along with a bias, which always has an input 1. Okay, and now here, each and every neuron that you look at, let me take example of this neuron. Okay, each and every neuron will have 2 components. Those are summation and activation. This summation part is actually called as integration component or integration function. And this part is called as activation function. Activation function. All the neurons except for your input layer neurons will have 2 components, integration component and activation component. Usually the integration component which is used is summation. Very, very important. If you understand this, I'm sure you'll understand the rest of the program in a very easy manner. Okay, so please pay attention, friends. Summation means what's happening here. Let's see. B into 1 will be B plus W1 into X1 plus W2 into X2 plus W3 into X3 plus W4 into X4 plus W5 into X5. This is the sum product of weights with the inputs, and you're doing that summation and you're integrating all these together. These circles that you see are called as neurons or nodes. Neurons or nodes. This is also a neuron or a node. And these other connections that we have, connections, edges, vertices, all mean the same. Once you take the summation component, you pass it to your activation component. You pass on to your activation component. And in this scenario, there is some activation component which is being used. And I'll first explain this, okay? This is called as a step function. And these activation functions here actually will bring in something called as non-linearity aspect, meaning they capture the non-linear behavior also. But we'll get to that later, okay? What do you mean by this step function? How is it going to work? Say you do a sum product of all of these, or you do an integration, summation, and say you got 0.8. So what you do is, if this function, if it is greater than or equal to 0, then you will say output should be 1. Output 1 means maybe person will default on the loan. If this value is less than 0, then you say 0. 0 means person will not default. So you'll have all those not default, default, all those examples, and say you have 1,000 such examples. Examples or samples or rows all mean the same. Okay, and thereby you get an output. So you're just multiplying the weights with your inputs. Okay, and then you get a value. Take that value and supply it to your activation function. If this value is greater than or equal to 0, you say 1, else you say 0. So you'll either output 1 or 0. 1 means person will default, 0 means person will not default. Friends, please just give me another 20-25 minutes before you ask any questions, because I'll ensure all the doubts are clarified. Okay, pay attention here. Don't worry about the questions, just pay attention. For another 20 minutes, just hold on to your questions, because all those questions will get addressed now. Okay, please pay attention. Okay, so once again I repeat, if you have 5 inputs, you'll have 5 neurons plus one additional neuron called bias. These weights are randomly initialized. All these weights are randomly initialized. Randomly initialized. Okay, and then what happens is you'll have this error surface, error, and weights. Let me take one weight example and explain you. So the error surface will look like this. Initially, the weights are randomly assigned. Say when you have randomly assigned your weights, the corresponding error was this. This was your corresponding error. Then what do? You traverse forward, which is called as forward pass. You do this multiplication and then do this integration. And once you get a result, pass it to your activation function. Once you pass it on to your activation function, you'll get an output, which is called as your predicted value. Okay, which is called as predicted value. How did you get this predicted value? Say you have taken the first row, you have taken all these inputs, and you have passed all these inputs through your network, and then you got the predicted value. The moment you get the predicted value, try to compare it with this actual value. If both are the same, then you have no error. But if there is a mismatch, that means there is an error. Okay, I'll first take example of continuous output variable, not default, not default. Let me say you want to predict on what will be the salaries of people after this training, because you all are undergoing training in the most amazing field, deep learning. At least I can say data science is more or less becoming a commodity, but artificial intelligence and deep learning still has the niche. So you're undergoing the training in this. Obviously, you can command more salary, right? But what will be your salary is what you want to say predict. So you take all these inputs, pass through your network, and you predict on what is your salary going to be. And then you subtract it from the actual value. Okay, when you subtract it from the actual value, you get error. So predicted minus actual value will give you error. Okay, here for each and every row, you'll be getting errors, right? Then next, take the next set of inputs, pass it through your network, get the predicted value, subtract it from the actual value. You get the error second row. Then take the third row, pass it through your network, calculate the predicted value, and then take this actual value and subtract, you'll get error. Do you know what? You'll have 1,000 such error values, and each of these error function is called as loss function. Each of these errors is called as a loss function. So that means for every example, every sample, every row, every observation, the error that you get is called as loss function. Take all these errors and combine them, such as do a mean error, or let me put it somewhere here. Okay. If your output variable is continuous, then you can use mean error or mean absolute error or mean absolute deviation, mean squared error, root mean squared error, any of those. So you take that mean error or whatever be it, these uh, these loss functions, when you combine them together and get an aggregate value, it is called as cost function. Cost function. So loss function and cost function, that's the thin line of difference. Loss function is for each and every row. When you combine all of that and aggregate, it's called as cost function. We are discussing only when output variable is continuous. What happens when output variable is discrete? We will discuss. Okay, we'll discuss that. Now, please focus on output variable continuous. The moment you get an error, or I would say cost function, you go back, and then update your weights. So you'll now update your weights here. When I say update your weights, I'm not saying increase your weights. I'm just saying update, because sometimes you might also, your weights might also get initialized here. Then you'll have to reduce the weights to reduce the error, right? So you update the weights, and each time you update the weights, look at the error values, and then again update the weights and update the error values. Keep doing that. Keep updating the weights. So go forward, calculate the cost function or loss function, come back and update the weights. Again go forward, calculate your loss or cost function, again come back and update the weights. Each time you go forward and come back and update the weights, you're following or you're doing an algorithm, you're applying an algorithm called as backpropagation algorithm. Backpropagation algorithm. And why are you updating the weights? You're updating the weights to reduce your error. And here the algorithm which is used to reduce your error is called as gradient descent algorithm. Gradient descent algorithm. Okay, so please pay attention here. Gradient means slope. The rate at which your error is changing is gradient. And you want to reduce your errors. So you always want to come down the hill, come down the error surface. Hence it is called as descent. Right? Rate of change in the downward direction is gradient descent algorithm. Coming back and updating the weights, backpropagation algorithm. Actually reducing the error is gradient descent algorithm. Okay, now Let's remove this part. All right. So you might ask, or you might be having this question that why can't I get zero error? If I keep doing it, will my error become zero? Never. Why? Let me give you a basic example here that here on single input variable. Say you have an output variable and input variable. If your output is 4 and input is 2, if your output is 6 and 3, 8 and 4, 9 and 1, then how can I capture the relationship between y and x? You might say y is equal to 2 times of x, right? If I put 2 in this, you'll get output as 4. If you substitute 3 here, you get an output as 6. If you substitute 4, you get an output 8. But if I substitute 1, I won't get 9. So this equation is capturing the relationship of all these 3 patterns, but it could not capture this pattern. Obviously, right? So when you have data, you cannot be rest assured that your equation that you get will capture all these patterns accurately. It cannot. It will, in a generic manner, capture the relationship between y and x. Hence, since your underlying data would be different, you can never obtain an error of 0. Remember that. So this is very basic rudimentary stuff. You need to understand this, because a lot of people keep asking me on, if I keep doing this back and forth, will I not get 0? Never. Okay, because of the explanation that I've just given. This is when your output variable is continuous. But one more thing I need to explain you all is about gradient descent algorithm. There are primarily 3 algorithms. One is called as batch gradient descent. Another is called as stochastic gradient descent, which is also called as SGD. And the third one is mini batch SGD, which is also called as mini batch gradient descent. In each of these, we need 2 things. We need to know about 2 things. One is epoch and another is iteration. What do we mean by these? Okay. Batch gradient descent means I take each row, pass it through the network, calculate the predicted value, subtract it from the actual value, and then you get error. Take each and every row, pass it through your network, calculate the predicted value, subtract from the actual value, and calculate the error. And then take all these errors or loss functions and then get one cost function. Okay. And then once you traverse all your training samples through your network at least once, or once rather, you go back and update your weights. That is called as one iteration. And what is called as iteration? Each time you update your weights, it is called as iteration. But if you complete all your training samples by processing them through your network back and forth and update your weights, that's called as one epoch. Now let's look at stochastic gradient descent. Stochastic means noise, randomness, right? Randomness, noise, randomness. So what this means is you randomly choose any of these rows. Say you randomly chose row number 3. Take your inputs, pass to your network, calculate your error, then come back and update your weights immediately. So that's called as one iteration. Then next, take the next randomly chosen row, take all these inputs, pass through your network, calculate the error, come back and update your weights. This is called as second iteration. Why? Because you're updating the weights. Each time you update your weights, it is called as one iteration. And when do you call it as epoch? When you complete all these training samples, when you traverse all these training examples once through your network and come back and update weights, it's called as epoch. So if you have a single epoch, my question to you all is, how many iterations will we have? Given that in this epoch, I mean one epoch, and you have training samples of 1,000. So how many iterations will we have? Let me ask this question as a poll question. Okay, so in stochastic gradient descent, SGD, within each epoch, how many iterations do we have? 1 or 1,000? Or would it be 100? Please, can you all answer this? Please, can you answer that? Wonderful. It's 1,000. Great. Okay. So one epoch means you'll have 1,000. All these training samples should traverse through your network at least once. And in stochastic, when do you update your weights? As soon as each and every training sample passes through your network, you come back and update your weights, right? So how many times it happens? 1,000 times. One epoch has 1,000 samples here, and you update the weights each time one of the samples traverses through your network. So you'll have 1,000 iterations. Batch means the entire batch. Once it passes through, you capture all those errors, take the average error, come back and update the weights. That's batch. On another side, you have stochastic. This is at one extreme, and this is at another extreme. To strike a right balance between these two, we have something called as mini batch SGD. And let us discuss about this. In mini batch SGD, you mention batch size. If you say batch size is equal to 100, for example, then it will take these 1,000 and it's going to split these 1,000 into each of batch size 100. So 1, 2 until 100. This is batch 1. Then 101 until 200 will be batch 2. Then 201 until 300 will be batch 3. And in this way, how many batches will I have? If I have 1,000 total, and if each batch size is 100, then how many batches will I have? 1,000. Each batch size is 100. So you'll have 10 batches. So what happens is, why is it called as mini batch SGD? Because within this batch, first you take this batch, okay? You randomly process, say you randomly send row number 3 through your network, calculate the predicted value, take the corresponding actual value, subtract, you get error. Store it. Then process row number 100 randomly. Randomly you're choosing, not in a sequence. So you pass the 100th observation, you get the predicted value, subtract from the actual, you get error. Then take row number 1, pass it through your network, calculate the predicted value, subtract from actual, you'll get error. In that way, you'll get 100 errors, right? Error 1, 2, 3, in that way you'll have all the 100 errors. Take all of those, calculate, say, mean error, come back and update your weights. Then go to the next batch. And then once again, randomly choose a number, maybe 105, pass it through your network, calculate the predicted value, take the actual value, subtract those, you'll get error, come back and, okay, don't update the weights yet, sorry. So you take 101, say you have taken 105. Then next would be, say, 108. In that way, after all these 200 are done, you again calculate mean error, come back and update the weights. Each time you update the weights, it's called as one iteration. And when you complete all your 1000 once, it's called as one epoch. So if I have one epoch, how many iterations will we have in this? Okay, so how many iterations are we going to have? Let me ask this as a poll question once again. Reset, add a poll question. How many iterations will we have? Will it be 1, or will it be 1000, or will it be 100? Please, can you answer this? For this scenario, I'm asking you all to answer this for this mini batch SGD, given that you have 1000 observations and batch size is 100. Yep. How many iterations will we have? Wonderful, 100 iterations. Good. So you all have good understanding. Oops. I think I didn't give you the right answer here. Sorry. And you all are like, that's okay, kind of, huh? So let me give another number here. Sorry, please answer this. And now I'm pretty sure you all must be aware of the answer to this, right? So 10 iterations. Sorry, my bad. Why 10 iterations? Because after processing each batch of 100, you update the weight. So 1 time, 2 times, 3 times, 4 times, 5 times for all these 10 batches. So you get 10 iterations. Okay. So we will take a break. And once we come back from the break, we are going to discuss about what if I have output variable, which is discrete. Okay, what if the output variable is discrete? And that is what we are going to discuss. So let me erase these things. And let me also remove these. Whatever is not needed, I can probably remove. Let this gradient descent part be there, just in case you want to have a quick look at that. And we'll have 10. Now, what's the time? It is 11:36. Let us all be back by 11:45. And until then, we will have a break. Okay, break time. Take a break and come back, friends. So welcome back to the session, and let us understand more. Okay. So here, let us now take an example of output variable, which is continuous. Sorry, discrete. We already discussed about what if your output variable is continuous. Let me give a table for that. Output variable, then loss function, and then error function. Loss function or cost function. This is how I will mention, because loss and cost are the same, with the exception that loss is for a single row, cost is for all the rows. Okay. I would also like to just give more space to this. If your output variable is continuous, then your loss or cost could be mean error, mean absolute deviation or mean absolute error, mean squared error, root mean squared error, mean percentage error, mean absolute percentage error, bunch of those. And error functions are also the same. Error functions are used for model evaluation, right? Same things can be used. Mean error, mean absolute error, mean squared error, root mean squared error on similar lines. If your output variable is discrete, and if you have two categories, okay, then your loss or cost function would be called as binary cross entropy. We discussed already about cross entropy, right? I'll once again touch upon that. Binary cross entropy. And then when it comes to error function, you can use a confusion matrix or a cross table, and then you can proceed further. If you have output which is discrete, and if you have more than two categories, you use categorical cross entropy. And the same confusion matrix or cross table can be used. A lot of people associate confusion matrix with two categories. It can be extended. There is nothing wrong in that. Okay, and we have a lot of additional measures. That's fine. Let's stick to this and let us understand the scenario of cross entropy once again. If you have, say, an image of an elephant, I think I keep giving the same example. So you have a trunk and you have the legs of the elephant. Yeah, assume that this is elephant. Okay, don't worry. And say you're dealing with a 4-class problem. Tiger, lion, cat, elephant. Okay, say you have a 4-class problem. This is your actual data, actual class. If it's, I mean, if this image is elephant, you'll have a 1 here and you'll have 0 throughout. Means there is 100% probability that this is elephant. That is what it means. Actual data. You can represent this actual data as P. Give a notation as P. And say you have the predicted values also for all of these: tiger, lion, cat, and elephant. Once again, you have tiger, you have lion, you have cat, and you have, say, elephant. And this would give you the predicted values. So you have actual values, predicted values. If it is not tiger, sorry, say there is 10% probability that it is tiger, 5% probability that this image which is given is a lion, then 15% probability that it is cat, and 70% probability that it is elephant. And you give this a notation Q. Okay. Then entropy is given as minus summation of I equal to 1 until n. N is the number of classes that you have, into pi log of qi. Since you have 4 classes here, tiger, lion, cat, and elephant, you can mention as summation of I equal to 1 until 4 pi into log of qi. If you were to expand this, it will be minus p1 when I substitute I equal to 1, p1 into log of q1, minus, if you substitute I equal to 2, it will be p2 into log of q2, minus, if I substitute I equal to 3, you get p3 into log of q3, minus, if you substitute I equal to 4, you'll have p4 into log of q4. Okay, here 0 into log of 0.1 minus 0 into log of 0.05 minus 0 into log of 0.15 minus 1 into log of 0.7. Log of 0.7, if I'm not mistaken, will be I think 3.5 or something. So you'll just multiply this. This will be 0, this will be 0, and this will be 0, and you'll get a value here for this. This is called as loss or cost function. If it's for a single row, single image, it is a loss function. If you calculate for all the images, all these loss functions, and combine them, it will be called as cost function. Okay, just imagine, I mean, there will be some error. Just imagine that your predicted values were like this. Your model predicted that there's 0% probability that it is a tiger, 0% probability that it is lion, 0% probability that it is cat, and there is 100% probability that it is elephant. Then what will be the cross entropy value? 0 into 0 will be 0, plus, minus 0 into 0 will be 0, minus 0 into 0 will be 0, minus 1 into log of 1. Log of 1 is 0, so that will also be 0. So this value will be equal to 0 if you have perfect prediction. That means loss will be 0. Okay, this is called as cross entropy. If you have more categories, it is categorical cross entropy. If you have only 2 categories, it is called as binary cross entropy. And this loss is used to go forward, calculate the error, come back, and update your weights. Okay, now this is fine. This is all about your biological brain. A guy by name Frank Rosenblatt, way back in the 1950s, he has come up with this algorithm called Perceptron algorithm. Okay, and the learning or the concept which is used to update the weights was back then, I mean, it was being used heavily. It was called as Hebbian learning. Then Windroff and Hoff, two people in 1960s, they came up with another rule called as delta learning rule. And that's a rule which is used to update the weights. And this is what we are going to look at, right? We will look at this back propagation in action using a toy example. And if you look at this formula, you have this new weight is equal to old weight plus eta. This is called as eta, which is called as learning rate into error into your input. And this eta value or learning rate ranges from 0 to 1. And if you have an error surface like this, if you are here, if you choose an eta value which is very, very, very small, I mean, you need to decide on how many or on what should be the eta value. You need to decide. Okay. If this eta value is very small, then it would take infinite steps. It would take infinite steps for you to reach to your bottom of the valley or the minimum error. So you should not choose eta value which is extremely small. Neither should you choose an eta value which is close to 1, because if it's very high, it will just jump. And then you have just missed out the deepest of the valleys. I mean, you missed out an opportunity to reach the minimum error and you overshooted that. These challenges will arise when you have to choose your learning rate, and then people usually use some kind of grid search techniques and all that advanced concepts. Those are, we will not touch upon that. Okay, let me give this basic example, a toy example, in helping you understand about perceptron algorithm. Okay, there is a two class problem, red or a blue. Z equal to 1 means red, Z equal to 0 means blue. Okay, and you have the inputs wherein each, this has an input -1 and +1, -1 and, sorry, -1, and this will have an input -1 and 0.5, which is 1/2, and then you have 0.5, which is 1/2, and 1 here, and here also you have 1 and 1/2. Okay, you have all the inputs. Say you have chosen eta value as 1/3 learning rate, and initially the weights were randomly chosen as 0 and 1. Randomly they got initialized, randomly. Okay, 0 and 1. With that, say you got this as your classifier, this black line, this is your classifier. Anything which falls above the line is Z equal to 1, so this will be a right classification. Anything which falls above is this, which is again the right classification. This is also right classification, so anything below would be right classification. But if you look at this, this is misclassified. Okay, this is misclassified. Why is this misclassified? Because anything above should be z equal to 1 or red, but it's blue. So this is misclassified. Okay, and then formula to get a new weight is old weight plus eta into error into x. So only for this we need to update the weights. If you look at this, it is -1 comma 1 by 2. 0.5 means 1 by 2. And let's update. So new weight is equal to old weight. Old weight is 0. So 0 plus eta value, which is 1 by 3 into actual value minus predicted value. Ti minus yi, right? Ti is actual value. This is predicted value. Actual value is actually this is z equal to 0. But you predicted that this belongs to z equal to 1. So the error is -1. So you have this -1 into what is the input? It is -1 into -1. When you solve this, you get 1 by 3. That's your updated weight. Now you have to do it for this axis, this variable also. So you take that. And new weight is equal to old weight plus eta value into actual minus predicted is -1 into 1 by 2, which will give you 5 by 6. These are the new weights that you have. With these new weights, again, draw the classifier. When you draw the classifier, once again, this data point is misclassified. Misclassified. Anything which falls above is red, anything which falls below is blue, but this is falling above. So it's the misclassified value. Okay. So here, your new value is equal to old value plus eta into error into x. So here, new value plus eta value into true minus actual. Okay. Sorry, true minus predicted or actual minus predicted. So actually this is 0, but you predicted that it is 1 because it's falling above this line. And then error is nothing but -1. So -1 into you have -1 comma 0.5. So into -1, you get the new weight. Then update for the next one also. Take the old weight, new weight equal to old weight plus eta into actual minus predicted, which is -1 into your input, which is nothing but 0.5 or 1 by 2. And you get this. So these are the new updated weights now. Now, if you once again draw this line, now it's looking proper. So correction of weights turned out to be a rotation. And then now it's proper. Any value which falls above is red. Any value which falls below is blue. Okay, above is red, below is blue. And there is no misclassification, so your algorithm will stop. Okay, so again, just to do a quick recap, a neuron will have two components, integration component and activation component. You take the inputs, you process it through your neuron, and then you get an output. Until now, the algorithm that we have seen is good at identifying linear patterns. If you have like this, and say you have the crosses, if these two are two different classes, then you draw a line and classify these two, red and blue. You classify these as two different classes. Okay, linear patterns are identified using what algorithm? Perceptron. Using perceptron algorithm. But when you have a nonlinear boundary like this, and if you have it like this, then you cannot draw a single line and segregate these black crosses with pink circles. You cannot draw a single line. Hence, you need multiple lines. You need multiple perceptrons. One perceptron can handle only a single line. Draw multiple perceptrons, which will be able to handle the non-linear patterns also. You need multiple lines, multiple perceptrons. Hence, it is called as multi-layered perceptron or artificial neural network, which will handle non-linear pattern. So on one side you have linear pattern, on another side you have non-linear pattern. Okay. To handle the non-linear pattern, you can also change the integration function. To handle the non-linear pattern, you also have an option to change the integration function, such as instead of having the linear function, you can just make it quadratic by putting a square, or you can take x minus w whole square, input minus weight whole square, which will handle spherical, but people do not use this typically. Yeah. They simply use multi-layered perceptron. And within a multi-layered perceptron, you'll have your input layer. Okay. And you can have a hidden layer. And then you'll have an output. And each of these neurons will be connected to each of the other neurons. In that way, each neuron will be connected to each of the other neurons in the forward layer, and you get the output. How many neurons will you have in your input layer? Okay, for this, I have a poll question which you have to answer. Let's see. So let me run this. So here, if your data set has 21 inputs and an output, then come up, then how many neurons will we have in input layer? Will we have 21 or will we have 22? Let me see how many of you all were active and can answer this correctly. Let us see. Right answer is 22, friends. Why? because you'll also have another input called as bias. Remember, it will always have a 1 bias. So if you have 21 inputs, 21 plus 1, which will be 22. And when it comes to hidden layers, you can have as many hidden layers as possible. Your wish. If you keep increasing the number of hidden layers, your algorithm will take more time. Okay, but then it will learn all the representations properly. So your accuracy might increase. At the same time, it might also overfit your model. That is also another thing that you need to look at. Okay, you can either have a single hidden layer or multiple hidden layers. One hidden layer might have 3, another hidden layer might have 3, a third hidden layer might have 2, a fourth hidden layer might have 10. It depends. Okay, and then you have your output layer. So you have your input layer. You can have one hidden layer, or you can have two hidden layer. In each hidden layer, you can have 3 or 4 or 5 or 2 or 100, doesn't matter. And you have your output. When it comes to your output layer, if your output variable is continuous, okay, then you will have a single neuron. If you have an output variable which is continuous, okay, you'll have a single neuron. If your output variable is categories, you might have a single neuron, or you might have two neurons. You can have either one neuron or you can have two neurons, doesn't matter. If you have two neurons, say you want to predict whether a person will default on the loan or not. And if you have two neurons, then one neuron might say there is 92% probability that a person will default. Then obviously the rest of the another remaining 8% will be for the second neuron. It will say there's 8% probability that people will not default. Default, not default. Okay, that is how it is. If your output variable is discrete, and if you have more than two categories, I mean, you can have one or two, doesn't matter. It's left up to you. You take a call. What is the best practice out of these two? I don't know. Not just me, no one can tell you. Okay, you just try out whatever suits you. All right, next. If you have more than two categories, say you have four categories, then you'll have four neurons. One, two, three, four, in that way. Okay, if you have two, if you have four, it's like this. Okay, next. We have already discussed about activation function. Okay, within each neuron, you'll have two components. What are those two? Integration component and activation component. If the activation, if your output variable is continuous, then we use an activation function which is called as identity function or linear function. Okay, you use an identity function or a linear function when your output variable is continuous. All right, now that means whatever is your integration value, whatever is the integration value that you give as an input here, the same thing will go as an output. There's nothing that you do. Okay, there's nothing that you do. This is called as linear function or identity function. Step function we have already discussed. Step function means if you do this integration, for example, you have all these. Okay, you pass it through your network and you have an output, right? You'll have integration and activation. And you'll also have one bias B. Say this is x1, x2, x3, and you have weight 1, weight 2, and weight 3. Now, when you do this summation, if the value that you get is greater than or equal to 0, then the output is 1. If the value is less than 0, whatever summation, if you get less than 0, then the output will be 0. Okay. And here, if you do this integration, if you get a value which is greater than 1, then the output will be 1. If you do this integration, that is b into 1 plus w1 x1 w2 x2 plus w3 x3, when you do that, if you get a number which is in between 0 to 1, and if you get a value say 0.8, then output also will be 0.8. If you get a number 0.6, output also will be 0.6. That's this part, the linear part. It's like a linear function. And if you get an output here which is less than 0, negative numbers, then you'll say output will be 0. This is another function called as ramp function. All these functions somehow will be capturing the relationship between your output and your inputs. That's it. You also have sigmoid function. The beauty of sigmoid function, I'll let you know. The disadvantage with these two functions, in the good old days, people started like this. Okay, just because they are there, we are learning. But now things changed. So if you have a sharp bend like that, or if you have a sharp bend like this, then you cannot differentiate at this points. You cannot differentiate. Here also you cannot find the differentiation. Okay. At sharp points, since you cannot find the differentiation, you use a smooth function such as sigmoid function, which has a smooth finish. When you have smooth finish, you can find the derivative at these points. We'll learn about that later, okay? Don't worry at this point of time. So here you have sigmoid and tangent. These two are from the family of logistic. Okay, they're called as logistic family of curves. Then the most widely used in the current world is ReLU and its family. ReLU stands for rectified linear unit. Okay, you have rectified linear unit and family of that, such as leaky ReLU, ELU, etc. Now, you will once again have the same thing wherein you have your input, output, you supply this, you'll have integration, and then you'll have activation. This activation, if you use ReLU, for instance, what happens is, if you get the summation value which is less than 0, that is if you get minus 0.6, then the output will be 0, because this is a function which is used here. If you say what is the maximum out of 0 and minus 0.6, obviously 0 is maximum. If you take the scale 0, 1, 2, 3, minus 1, minus 2, minus 3 in that way, 2 is bigger than 1, 1 is bigger than 0, 0 is bigger than minus 1 in that way, right? Hence, if you have negative values and 0, 0 is the max. Okay. And if you get a number which is positive, for example, if you get plus 0.6, then again you say, hey, out of these two, that is 0 and 0.6, which is a maximum 0.6. So that would be the output, right? When you use ReLU, this is what happens. And then a variant of that was introduced called as leaky ReLU, which says that if a number is negative, we are clipping it to 0 here in ReLU, but here, let us not make it 0. Let me take 0.01 times of that negative number. So I'll scale down the negative number by 10% and then I'll start using it. Okay. Yes. But again, the disadvantage with these two is that you have a sharp point here. Whenever you have a sharp point, you cannot find the derivative, because derivative, it becomes derivative at a single point. And we discussed that derivative at a single point means there won't be any change along x-axis and there won't be any change along y-axis. So y-axis change by x-axis is undefined. We discussed this. Same logic applies here. Hence what people thought is, okay, let us also address this issue by putting a smooth bend over there. Okay, the moment you have a smooth bend, you can find the derivative. The moment you can find the derivative, job done. Okay. And there is also something called as max out. Max out means you take the maximum of the two outputs. Simple. Okay. So for example, if you have a network like this and you have connections and W1, W2, W3, and you have X1, X2, X3. Okay. And say you have integration and activation. So what happens here is you look at W1 into X plus this bias. Okay. And you look at W2 into X plus bias, W3 into X plus bias. Okay. And what will be the output of this? Should be the maximum of these two or these three. You have three, right? Maximum of those three will be your actual output here. And this way people came up with various logics, various activation functions, such as state step function, unit step function, heaviside, sine, ReLU, leaky ReLU, parameterized ReLU, shifted ReLU, max out, noisy ReLU, soft plus function, exponential linear unit, sigmoid, tan H, combination of those two, which is called as swish, so on and so forth. Okay, but again, all these will just ensure that it captures the patterns between your y and x. That's it. That's the underlying logic. And here, if you have a network like this, and say you have an output layer with 3 neurons, and if every neuron is connected to every other neuron, okay, if every neuron is connected to every other neuron in this way, then this is called as dense network or fully connected network. It's called as dense network or fully connected network. And then you have 3 outputs. Okay, and then you have 3 outputs here. So why do you have 3 outputs? Let's see. Because you want to maybe classify on whether a given image is tiger or cat or elephant. Then you'll have 3. But the values which come out from these 3 might not add up to 1. Hence, what people do is for the last layer in the activation, if you use something called as soft max in the last output layer neurons, if you have multiple categories, if you use soft max, it will do some mathematical calculation and give you probabilities as output. Okay, you take those probabilities and then you choose on which is the maximum value out of these three. What is the maximum probability? That is what you look at. Okay, and then when you add all these probabilities, they will actually sum up to 1, because summation of all the probability values should be equal to 1, right? That is the reason. Now let me also explain this. You randomly initialize the weights. Okay, when you randomly initialize the weights, you come down the slope. If you randomly initialize somewhere here, you might go down here. If you randomly initialize here, you might go down here. So where your weights are randomly initialized would decide on what will be the error or loss that you're going to get. Will you get a better result or substandard result? Depends on where you initialize your weights. This kind of solution is called as open form solution, because you have multiple solutions to this. Okay, so you have multiple solutions. Here you have a closed form solution. Closed form solution. Closed form solution means you will have a single output or single minimum value. That's it. It's called as a global minima. If your weights are initialized here, you keep updating your weights and keep changing your error, and at some point you will reach the minimum. Okay, at some point you'll reach the minimum. This is the only minimum which is possible. You'll not have multiple minimum values like this. You'll have a single minimum. That's called as closed form solution. But when it comes to neural network algorithms, you'll not have a closed form solution. You'll have an open form solution only. Okay, look at this. Weights got initialized here. So step by step you're updating and going here. If your weights get initialized here, step by step you update and go here. So how you initialize? Based on that, you go there. And weights are initialized randomly, right? Initially. So you have no control on where it gets initialized. However, having said this, you can run the algorithm multiple times with the hope that at one of these initializations, you will reach the minimum error surface. So you can do multiple iterations kind of. Now, let us understand the multi-layered perceptron algorithm. Okay. And I think it is logical time to take a quick break because it might get too theoretical otherwise. After this, I'll just briefly introduce you all to an algorithm in R. Okay. And then we'll switch to Python. But for now, let's quickly take a break. I think it makes sense. It's almost 12:30 now. So let us take a break until 12:40 and then we will continue. Yep, please take a break and come back and then we'll continue, friends. Hello, everyone. Thank you, Shakina, for that update. We have a lot of functionalities which we have not actually made it live for everyone. Okay, so I can speak about that. The functionalities that we are including here are as follows. Okay, it's there for a few of the people we have made it live, but not for the other people because we want to first ensure that it is completely tested. While you're watching a video, say we place the video on our learning management system, and you play that video and you're watching that video, and suddenly there is a question that you have on, okay, you're explaining about learning rate. Is learning rate and step size the same? Okay, it's a recorded video, mind you. So what do? Either you go to Google and search, or we are going to give you an AI driven chatbot here. You just, there'll be a speech system which is enabled. You talk with the system and ask. You just like a mic, right? You press that and then say, hey, what is the difference between learning rate and step size? Immediately it would respond back saying that both learning rate and step size mean the same. Depending on your learning rate value, which ranges from 0 to 1, the step size varies. Okay, step size varies. If you give a value which is close to 0, then the step size will be small. If you give an eta value or learning rate value which is very high, then the step size will be high, big. There'll be a big size. Right? This is about your speech recognition system. Or you can type in your question and it is going to respond back immediately on the fly. If you ask if there is a video on deep learning primer, okay, and if there is a question that you ask about, say, convolution neural network, then your chatbot will respond back saying that, do you know what? CNN is a concept which is covered in module number 6. It gives you this kind of response. So you know that, okay, it will get covered later on. Exactly like what a tutor would respond. On similar lines, our AI driven chatbot will respond. Another functionality that we have here is, say you're watching a video, recorded video, you'll have an option to enable the webcam. You can enable the camera, and this cam is going to capture your behavior. Say you are watching that video and suddenly you get a call, right? You're watching that and you got a call. What do? You answer that call. It will record that, okay, while you were watching the video at 14th minute, okay, you got this call, and until 20th minute you were on call. So you missed out this portion. You might not be active in listening to this portion. At the end, it will give you a report saying that, congratulations, you watched these 120 minutes of video. Out of these 120 minutes, 14th minute to 20th minute, you were disengaged, right? 14th to 20th minute, you were disengaged. Since you were disengaged from 14th minute to 20th minute, right? Do you want to watch only this portion of the video? Then click on that. Click on this. It will take only to that portion. Watch that part and job done. So your learning will become amazing. And finally, what we are doing is, if these videos are my sessions, my recorded videos, then you'll get a photo. You'll get my face. Instead of a chatbot, you'll get my face cut out like that. Okay, and when you ask a question, you'll feel as if I'm responding to you. That's augmented reality. Except for this part, remaining parts are already available and our participants are using those functionalities. Only this part, there is a problem with the lip sync of this image, and then we are working on that. Hopefully by this year and this functionality also will be ready, but these things are already live, friends. And that is why we call this as AI Spry, artificial intelligence Spry. Okay, and then of course this will be translated into mobile app and all that. But then first of all, the heart is being built. It's like a baby, right? What gets formed initially for a baby? Heart gets formed. That's what we are forming now. And slowly and steadily the baby will grow. Hands, limbs, etc. Yeah. It will take some time, but then these features that I've just spoken about, which includes speech recognition, behavioral analytics, language translation, it's already live. Okay. Ah, auto ML. In order to create auto ML, you need to learn AI concepts. KNH, that's my answer. Yeah, people who do not upskill will lose the job, certainly. Is it possible to develop a regression equation using machine learning or deep learning with the given data? That question itself, I did not understand, Dhananjay. Okay. What do you mean by is it possible to develop a regression equation? Regression is a different model, right? Different math. Okay. And regression analysis is part of machine learning. Deep learning is a different concept. So I think you're getting confused. That's, you're getting confused, simply put. Yeah. So just let's get back. All right. So here you have artificial intelligence, and then you have data science, you have data mining. Within that, you have machine learning. Within machine learning, regression analysis is a small module of machine learning, and you have deep learning, which is another submodule. Now, within machine learning, you have regression analysis, which has linear regression. Okay. Linear regression is a different technique which will capture the relationship between y and x. Neural network has a different way of capturing the relationship between y and x. Machine learning algorithm means it will capture the relationship between y and x, output and input. The way the relationship between output and input variables is captured is very different. Linear regression has a different way to capture. Logistic regression has a different way to capture. Multinomial regression has a different way to capture. Ordinal regression has a different way to capture. Decision tree has a different way to capture, right? So hope the Dhananjay, you need to have the basic understanding foundation very right. Okay. Now let us proceed further with this. So one thing is, I am now going to use this kind of a neuron, okay, just for notation purpose. I'm going to combine integration and activation together, and I'm going to use a single notation. When you say this notation henceforth, that means it is combination of integration as well as activation. Okay, let's take this example wherein we have, say, two neurons, two inputs, and one output. Let us take this example. Since you have one output, you have a single neuron here. This has two hidden layers. One hidden layer has three neurons. This hidden layer has three neurons. And this hidden layer has two neurons. And you have an output layer. So you have input layer, and you have an output layer. Input layer has two neurons because you have two inputs. Output has single neuron because that could be a continuous output or a discrete with two categories. Now let's proceed further. If you have two neurons, then you proceed in this way. And here, initially weights are randomly assigned. And this has what? Two components, integration, activation. So W1 into X1 plus W2 into X2 will give you the integration component. Pass it through your activation. And the moment you pass it through your activation, you'll get an output called Y1. Okay. Now, here also you have integration and activation. So you take this weight into this input, this weight into this input, and these weights are also randomly initialized. Randomly you choose some number. Your algorithm will choose some number randomly, okay? So it's W1 into X1 plus W2 into X2. This is the integration component. Pass it through your activation component, and then you get output Y2. Then you proceed further with the next one, wherein you have W1 into X1 plus W2 into X2. When you do this component, solve it, you get the integration component. Take that and pass it through your activation, and you get Y3. Then what you do is you proceed further, wherein you say all these weights are again randomly assigned. W1 into Y1, W2 into Y2, W3 into Y3. You get the integration component. Pass it through your activation, and you get Y4. Then W1 into Y1, W2 into Y2, W3 into Y3 will give you the integration component, this component, and pass it through your activation here, and then you get an output which is Y5. Once again, these weights are randomly assigned. This weight into this plus this weight into this will give you the integration component, this component. Take that and give it to your activation. When you do that, you'll get the final output, which is your predicted value. Once you get your predicted value, take that predicted value and subtract it from the actual value. This is your actual value. When you subtract the predicted and actual value, you get an error. Take that error. I mean, what you have done is you have done a forward pass. Now do a backward pass, backpropagate. You backpropagate, and since you have an error here, what do? It is something like this, okay, on a jovial note. Say your principal, okay, and your head of department here, you are doing a presentation to your principal, and each of your department heads Okay. Say you're head of all the departments, and each of your department heads have certain people who are working under them, and then everyone together have given you some report. And then principal was unhappy because somewhere you presented wrong information, error. So principal will shout at you. Then what will you do? You'll take it back, right? Right? No one will be kind to each other. So what will you do? You will go back and shout at the individual head of departments, maybe. Okay. And then the head of departments will say, okay, I shared with you only so much information. Then you as head of department will say, okay, I will only shout you so much. Okay, and I'll only shout at you so much. So you take this weight into this error, and so much proportion of shoutings you give back. Okay, and then the next head of department also, you will go back and say, hey, what are the data? What is the data that you have given? You'll say, okay, I've given you so much. So much of shoutings you take back because of you, principal has shouted at me. Top down approach. Then in that way, your head of departments also will not keep quiet. They'll go back internally to people who have given them the data, and then they'll shout at them. How much? Take this much into this weight plus this much into this weight, because this guy will get the shoutings from this head of department and this head of department because he has given data to both of you. That will give you an error proportion to this. Then again you go to maybe finance department, and this finance guy has given data to two head of departments. Both of them will shout. How much? They will shout based on whatever information has been given. And then you get this. Again, this time say you go back to final department, you complete your shouting and all that. Then people will rectify it. They'll say, okay, let me rectify, let me correct the mistakes. And how do you correct the mistakes? Old weight is equal to new weight plus learning rate eta into your error, okay, into your input. That's it. So when you solve this, you get the new weights. That's the formula. So what is the rate of change is derivative. How much is the error changing when I update the weight? That's this derivative. Okay. Now we have already seen yesterday. These are the reasons, my dear friends, on why we have seen all these things. Okay. So this way you update, you again update the weights, you again update the weights, you again update the weights, and again calculate the error. If there is again error, again go back, update the weights the way I have shown you. Okay, and this process will continue until you reach the minimum error possible. Okay, quickly. There are different architectures and network topologies which are possible. Here, if you look at this, this is your input layer, which has 5 neurons. Here you have a hidden layer with 3 neurons. And here you have an output with 2 neurons. So this is your input. This is your hidden. And this is your output. Input, output, and hidden. Here also you have input, hidden, hidden, and output. Okay, you have an input layer, hidden layer, output layer. Question to you all is, you have two architectures here. On left, I have one architecture. On the right, we have another architecture. Which of these is called as perceptron and which of these is called as multi-layered perceptron? So I'll ask this as a poll question. Please answer. So which of the following is perceptron algorithm? Left hand side or right hand side? Yep. Please can you answer? Which is your perceptron algorithm? Left hand side or right hand side? Let's see. Wonderful. Left hand side. Exactly. Why? When it comes to your perceptron algorithm, you will have input layer and output layer. There won't be any hidden layer. Okay. So perceptron is used to handle linear boundaries. And second thing is it will have no hidden layers and it will have a single output layer. This is perceptron. And on the right hand side, you have MLP or ANN, multi-layered perceptron. I think someone has unmuted themselves. Enoch, can you please check? Maybe you have unmuted yourself.
Yeah,
Enoch,
it's
please.
on. It's off.
Yeah. So you have the data here. And if you have three inputs here, x1, x2, x3, then in your input layer, you'll have three neurons. Okay. And in the hidden layer, as I've told you, you can either have a single hidden layer or multiple hidden layers. You can have 1,000 neurons or 100 neurons or 1 neuron in your hidden layer. Doesn't matter. Okay, it depends on you. And you need to experiment. And you have an output. Okay. So MLP is used when you have non-linear problems. Perceptron is used when you have linear problems. Okay. Second thing, you can have as many hidden layers as possible, as many hidden neurons as possible. You have an output, etc. Now, if the output is continuous, you will have a single output neuron and you'll have linear activation function. Okay. If your output variable is discrete in two categories, then you will have either a single output neuron or two output neurons. And usually people use sigmoid activation function. Then if the output variable is discrete in more than two categories, okay, if the output variable is discrete in more than two categories, then if you have say 10 classes, then you'll have 10 neurons and you use something called as softmax activation function. If you remember these things, I think it should be good enough. And a single word when it comes to deep learning is experiment. There is no free lunch theorem saying that use this, use this, use this, use this, and you'll get the best result. No, unfortunately, there is no such option available. The only way out is for you to experiment. And we have TensorFlow. Okay, TensorFlow is a deep learning library which was introduced to the world in 2015 by Google. It became famous because it is from Google, simply put. Yeah. And this is a low level programming language, meaning you need to know very, very detailed programming to be able to write program in TensorFlow. Many people felt that, you know what? Why should I know so much of programming? I'm solving a business problem, right? I'm not here to do program. I'm not a programmer. I am a data scientist or AI expert. With this logic, in 2017, around that time, there was a guy called as Francois Chollet who has come up with Keras. Keras is also another deep learning library, which is called as high level programming language. High level programming language. This is very easy for anyone to understand. Even people with a little bit of programming knowledge can actually use Keras. Okay, and then they can solve it. And today there is something called as PyTorch, which is fast catching the attention of the world. I can show you this on Google Trends. And here we have TensorFlow, which is not a software per se, but that's okay. I'll use this TensorFlow. Then I'll search as Keras, and you have something called as PyTorch. Okay, this is in United States alone. If you look at worldwide, for the last 12 months, or you can actually pick for the last 5 years, yes, Google started, and TensorFlow started way back in 2015. So, yep, obviously there was high demand. Then you have Keras. Keras started picking up because people kept feeling that TensorFlow is no longer needed. So look at this. There is huge gap, huge gap. Gap is reducing, 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 and then at this point of time, gap reduced significantly. Okay, and PyTorch also earlier there was a huge gap, huge gap, huge gap. Gap kept on reducing, and today as we see, there is kind of an overlap. Okay, this is when I choose those specific things. I can just say TensorFlow as a keyword. What is the demand? Keras as a keyword. What is the demand? PyTorch as a keyword. What is the demand? Then you'll understand that Keras is having more demand than TensorFlow as a keyword. And then here you have PyTorch. Okay, so Keras is very, very high in demand. Okay, in almost all the places, right? Look at that Keras. Hmm? Overall, it is good on an average. And then here is the data. TensorFlow heavily used in China. Keras also is heavily used in China and also in a few of the ASEAN regions, such as maybe Malaysia, Indonesia, right? So on and so forth. And PyTorch also is okay, kind of, it's picking up. Okay, this is how it is stationed. The demand for TensorFlow, for Keras, and for PyTorch. We will be making use of Keras libraries to build our applications. Next thing, the beauty of Keras is that you can use Keras on, this is kind of your front end. And you can use it on TensorFlow, Theano, CNTK, any of these backend systems which requires thorough programming knowledge. Okay, and then these algorithms run on GPUs or CPUs. GPU stands for graphical processing units. CPU stands for computing processing units. So the good part is this can work on GPUs. That means it can make your algorithms faster. And is this deep learning a holy grail which can solve any kind of problem? Answer is no. Okay. Most loss functions are non-convex in parameters, meaning there is no one defined solution. If I draw like this is a solution, this. There are many minimum surfaces which exist. Second thing is different initializations. If you have like that, if your weights are initialized here, you'll get here. If your weights are initialized here, you'll get there. So there are different local minima which are possible. There is also lack of interpretability. Lack of interpretability means when you have your equation like this, b plus w1 x1 plus w2 x2 in that way, the weights that you get or the bias that you get, these numbers cannot be interpreted. There is no meaning for that. But when you look at your regression techniques, each of these coefficient values, okay, each of these coefficient values will have some interpretation. But here we'll not have any such interpretation. Ablation methods with various arguments, meaning you have to decide number of hidden layers. You have to decide upon number of neurons in hidden layers. You have to decide on which activation function should we use. Okay, there are various weight initialization techniques. You need to experiment with all these combinations. Okay, you need to experiment with all these combinations basically. So which combination is going to give you the best result? No one knows, right? So you need to experiment. Until and unless you experiment, you don't know. Lack of easy reproducibility. That means, say, You ran your algorithm for the first time and weights got initialized here. So ultimately you reached this particular error, which is a minimum error given that your weights initialized here. When you run your algorithm again, maybe your weights might get initialized here. So you'll get to this error surface. If your weights next time get initialized here, you'll get to this. It is not guaranteed that each time you're going to get to the minimum of the error surface. And there is one more thing which is called as explainable AI. Okay, one more thing which is called as explainable AI, meaning you give the interpretation which is not there currently, but then US military defense department, which is called as DARPA, they are working on this, and certainly when they embark on some journey, they are going to make it a reality. No doubt about that. Yeah. So that's where we stand. Let us do a quick recap. We started off and discussed about AI applications. Okay. And after your AI applications, we have looked into machine learning primer. All that you need to know about machine learning. Then we discussed about mathematical foundations. And we have discussed about today deep learning primer. All the foundations that you need to be able to proceed further with practical work. Tomorrow, first half, we are going to discuss about deep learning practical challenges, and then we will run our first deep learning algorithm, which is your multi-layered perceptron algorithm. We will briefly use R, but then we will quickly do the same thing in Python, and from there on it will be all Python. And when we use Python, we will use Keras as the front end, and we are going to use TensorFlow as the backend. Keras front end, TensorFlow backend. Post this is done, I mean, tomorrow I think we'll be spending significant time on these things. Okay, and then tomorrow I will tell you on what we will do the day after that. So it will be, we will take a specific business problem, and we will look into how do we solve it. And when we try to solve it, we are going to follow project management methodology or approach. We'll follow this approach. We'll understand the problem, we'll collect the data, we will clean if needed, then you perform machine learning, and then this is how we are going to proceed further. Okay, and the last 10 minutes we are going to now dedicate to question and answers. Yeah. We'll discuss that tomorrow. We'll discuss that Sandhya later once we cover CNN. Yeah. No, you need not have any programming knowledge because I'm going to train you right from scratch. Yeah. Don't worry. And a few of the questions are very generic. Our team is going to respond. So here we go. People who have not received learning management system access, please check carefully your promotion tab in Gmail and spam folder. If not, drop an email to Prasad. If you do not receive a response from him within 24 hours, then forward that email to me. And I think yesterday quite a few people have sent me emails, and we have ensured that we give access to everyone. You keep experimenting, Kaushik. We will integrate it, Kutta, using web applications. Like, are you a web developer? We use Python Flask. Basically, you can use that and integrate. Regularization methods we'll discuss tomorrow. We can predict runoff from railway with that. To explore more about algorithms and research point of view, suggest links. Sure. Usman, you have to look at the recorded video once again. Vanilla activation functions you choose randomly and then you experiment. The best are ReLU. If output variable discrete, what activate? Okay, Sheikh, you have to watch the recorded video once again. Um Data frame is all about capturing the data and presenting it in a tabular format. Sai Dhanush. File can be in a text format also. If weights keep on changing, when we can say that we got optimum solution? When you get the minimum error, Badrinath. How to decide the number of hidden layers? It is experimental, Bharti. Then how to access the content in AirSpray? Drop an email. This is the screenshot. Watch the recorded video, go to this portion, and then you act accordingly. Attendance link not visible. Not sure why. It's there on the sticky note. Please log in from your email. Of advanced training. Please explain cybersecurity use cases. We have cybersecurity analytics, Rajkumar. You can enroll for that program. I would like to know the algorithms which comes under. I didn't get that. That's not research area of ML and DL. We'll talk about that on the last day of the training. How to initialize weights? Those are randomly initialized. And then now SVM is out of scope, Bhavya. That would not be explained. Can you please explain confusion matrix? So Shirisha, just go back to the recorded videos and watch it. It's the same thing. From where we will get datasets for experiment. It's there on internet. You can download. There are many openly available things, Vikram. But whatever datasets we use, we will share it with you so that you might take it further. It is automatically initialized, Kaveri Satish. I would like to know the algorithm which comes under supervised deep learning. Yeah, it's there on our slides. You can watch those slides on learning management system. I think the first day slides or second day slides will have that. You can watch that. Will there be common convergence if two scientists apply? No, there won't be, Sridhar, because it randomly initializes the weights. When I'm adding layer, the error is increasing, sir. Fine. That could be because of your regularization techniques you need to apply. Maybe you're using wrong activation functions. Um, if you're getting any error, please look at this and drop an email to Prasad. And if not, if he's not responding, then you can escalate to me. Will there be common convergence? No, there won't be, Ratna Kumar. Okay, Madhu, you might want to go back and check your recorded videos. I explained that at least 4 to 5 times, Madhu. Difference between AI, ML, and DS. Just have a look at that. And then what are performance metrics for DL? You have just now looked at, you use mean squared error or some kind of accuracy measures. And on the machine learning primer, we discussed about that in depth, Kishore Raju. Please watch the YouTube recorded videos. Do you have any limit to set weights? No, there is no limit as such. Yeah, the data set will be shared for practice. Keras is high end and TensorFlow is low level programming language, KNH. Then, yeah, three level classifier also, it's the same thing. Just draw a plot and then proceed further, Shirisha. What big deal? I mean, I'm sure you are very knowledgeable to do that. Two, you have to just add another column and another row and you'll get it. When do we stop the iterations in backpropagation? When it reaches the minimum error, sticky note is not visible. Will we have hands-on? Yes, we will have hands-on. Pratibha. Boosting is about combining multiple decision trees, and neural network is a black box learning algorithm. How to use TensorFlow? That is out of scope, Jagadish. Is it better if your team to help with quiz? No, that will not be done, Sai Dhanush. And that's just for your practice. That's it. How can I get the data sets? We will let you know when we practice on the data sets. Okay, please connect using your desktop and you'll be able to see that. Does weight depend on input? It's randomly initialized. It depends on nothing. But then after that, when you update it, does. Can you use MATLAB? Mahesh, you can use, but nothing comes close to Python. Okay, Python is number one. Weights are recalculated, same in both. No, it's calculated in a different way. Okay, then we have ADA boost, we have gradient boosting, we have extreme gradient boosting. All these have different way of updating weights. Okay, sticky note not visible. Can please. Thank you so much. Random variables for in the list. Random variables can be between minus infinity to plus infinity, Pushpa. Okay, but tomorrow we'll learn about that. How do we know that it's a maximum? We have done it in mathematical foundations, Puvirasi. You can check that. Curves if saving profits is very much high. So what can be the curve? It can be an exponential curve. I mean, number of inputs depends on inputs. Yes. In ASPRI, is there that downloading anything from the website causes? Yeah, yeah. Please don't download anything. Okay. Only data sets we are going to provide you that separately. Yeah, you can use Google Colab also, Bharati. That's absolutely fine. Number of it depends on inputs. Yeah, number of weights depends on number of layers, number of hidden layer neurons, etc. There is no way to the regularization techniques. Deepak Chaudhary, you use regularization techniques to overcome that. Yeah. All right, friends. I think we are good. So please fill in your attendance form. I think I'll have to share it attendance form once again. There we go. Thank you. Thank you so much. Have a great day and please watch the recorded videos so that you get a better understanding. Yeah. Thank you all.